Hello, this is Philip Myers of PEMY Consulting. This is the first of several videos that cover the use and practice of engineering units. I find that most textbooks don't adequately cover them and leave the reader confused about their use and manipulation. There are many systems of units in use today, but the two primary ones that we will be covering are the SI system for System International, the universal standard in science and engineering, and then the USCS, which is the U.S. customary system of units. There are others called British Gravitational, Imperial, English Engineering, etc. None of those have good firm definitions, and people use those in different ways, so we'll just stick to the term USCS. The practicing engineer must be familiar with both SI and USCS units, and we'll cover that in these videos. All of the units of interest are based on Newton's second law, F equals ma, so we'll brush up on that as well and show why it is so important with respect to units. Metrology. It's a word that has its roots in the Greek word metron. So you'll hear words like metric, meter, metronome, measure. All of those are rooted in this word metrology. Metrology means the scientific principles of measurement. Pause the video and take a few minutes to look at these bulleted items. If you have a good understanding of each of these bullets, then you don't need to watch the rest of these videos. If you don't, then it would be well worth your while as a plant or a tank engineer to go through these videos. Well, here we have a micro horror show for you with the evil character G sub C. G sub C, you probably recall from college, is a conversion factor that is supposed to help you with units conversion. While it's not wrong, it's not needed. It's an artifact that just increases complexity, and you have to remember how to use it. So I will show you the principles of not using G sub C, which is what I recommend, but if you choose to use it, that's fine too. So let's take a simple plot. We want to measure the area A equal to length times width. So the dimensions are length squared equal to length times length. You can see 1 foot squared is equal to 1 foot times 1 foot. That's pretty obvious. It makes sense. The most important point is that this is dimensionally coherent. So a coherent system doesn't introduce factors, unlike the next equation where we have SI is equal to 1 over G sub C times the first length 1 foot times the second length 1 foot, which is 1 square foot divided by G sub C. This is an incoherent system, but it works, and some of the in fact, the USCS system is incoherent. The conversion factor G sub C, which I just made up, is defined as feet squared per 144 SI. Now you can think of an SI as a square inch. The SI is 1 over G sub C for a 2 foot by 1 foot object. So you would take 2 feet squared divided by this G sub C factor and end up with 288 square inches, which is the correct answer. My point here is that you don't need to worry about a conversion factor G sub C. Just take, you want the area in square inches, so it's 2 feet times 1 foot. You get 2 square feet, and then you just multiply by the 144 SI per square foot. And there's no doubt about whether you use this or the reciprocal, because the feet have to cancel out, and you want to be left with SI in the numerator. So you get 288 SI, which is also 288 square inches. In the SI system, force is a Newton. So the basic unit of force is a Newton. It's not the kilogram. And as you'll recall, F equals ma is Newton's second law. We'll get into that in quite a bit more detail in later videos, but F equals ma is fundamental to how units of interest are used and manipulated. By the way, the Newton is defined as 1 kilogram accelerated at 1 meter per second squared. So it's the force required to take a kilogram and accelerate it at this acceleration of 1 meter per second squared. Note that this is a coherent system definition. So you can write 1 Newton because it's a shorthand for kilogram meter per second squared. Incidentally, a small apple weighs about a Newton. They're 4.5 newtons per pound force. So an apple, like the kind that fell on Newton's head, is equal to about a Newton of force. All of these properties that you see are commonly used in tank engineering. We're going to discuss all of these, and there are many others, but we won't go into those. There just isn't time. Now, the most important point probably to make is the motivation behind learning and correctly using units. It's amazing that there were some fatalities caused by this crash of Korean Airlines because there was confusion about whether the distance from the ground to the plane was in meters or in feet. Here, 5 people were killed and 40 were injured. In 1999, NASA lost a $125 million satellite orbiter. And what was the cause? None other than misunderstanding of units between 2 different groups within NASA, one of them using the English system and the other using SI systems. So again, this is more motivation for careful and proper use of units. Probably one of the biggest hazards when doing any kind of calculation is units. You can get an error of magnitude 32.2 if you do or don't use G sub c, the conversion factor, when it's appropriate. So failing to take units seriously can lead to all kinds of problems, not to mention that there are many other ways to screw up calculations. Just to reinforce this point, I want to give you my own experience. I was a new engineer sizing steam coils for a vaporizer in a liquid ammonia process that was used for making ammonium nitrate. I used pounds per hour instead of pounds per minute. Nobody was checking. I wasn't rechecking my work. When the system was installed, the entire plant was running at a small fraction of what it was supposed to be running. Of course, it was quickly realized that the steam coils were too small, and it was a humiliation and total embarrassment. I'm surprised I didn't get fired, and I don't really have a good excuse other than to say that units were never beat into my head in school, and even more important, I wasn't used to the idea of doing reality checks against your own common sense, thinking about the magnitude and the number and seeing if it squares with common sense. So here is what you should know and what we've learned in this unit. Improper use of units can be deadly, or they can cost you big time. We can handle units without reliance on the G sub c, and I recommend you forget about G sub c. The basic unit of force is the Newton in SI systems. We'll talk about both US, CS, and SI extensively in later units. And of course, underlying units is a must for understanding F equals ma, which we'll also do. Thank you.